Okay, good afternoon, everyone, or good morning, or good evening, depending on where in the world you might be. My name is Brodie Fischbacher. I work at the New York Stem Cell Foundation. I'm going to speak to you today about a kind of modular deep learning workflow that's been built at NICEF for the automation of verifying monoclonality in cell lines. So just to give you a little bit of background on the New York Stem Cell Foundation, we are a non-profit based in Manhattan with the mission of accelerating cures for the major diseases of our time through stem cell research. So we obviously have multiple teams working on multiple areas of disease research. And one of our biggest teams, of which I am a part myself, is the NICEF Global Stem Cell Array team, which is kind of the team that works on our robotic platform for the automated derivation of induced pluripotent stem cells at high throughput. And one of the important steps that we often use in the array is to monoclonalize, which just refers to the isolation and subsequent expansion of a single cell which has been derived from a cultured population. There are a number of reasons we might want to do this, and most of them have to do with minimizing or eliminating technical variability in one form or another, which may have been introduced during the reprogramming process or during gene editing or some other activity at NICEF. And the big one for the pharmaceutical industry at large, obviously, would be monoclonal antibody development. So we have an example here where we have iPSCs which have recently been reprogrammed from blood, and we have a kind of healthy subpopulation and an unhealthy one, and the idea is to separate the good ones from the bad ones. The issue is that it sometimes goes wrong in various ways. So for example, you sometimes get cells dying after FACS sorting. Other times the colony will differentiate, so it loses its pluripotent status and it's no longer desirable to us. Or you can get multiple cells being erroneously sorted, so you're left with a polyclonal mass of cells in your well. So historically we've had to verify that the well contains what we hope it contains, and that's mostly been through manual image review, which is not only time consuming, but once we kind of distribute this and scale it up amongst multiple research groups, it becomes a fairly critical source of technical variability, given that each person treats data differently. So the question is, can we automate the process as a means of standardization? And the immediate turning point would be deep learning, obviously. But we have a novel problem in some ways in that the labels we wish to assign are multi-image entities. So we can't simply take like a ResNet 50, assign semantic labels to single images and fit the data on that basis. So we have to kind of be a little bit more innovative in some ways. So we turn to detection networks, which are obviously useful given the dependence on count data in our case. And the first thing we've done here is to train what we call a global detection model, which detects colonies in a full well image. And we've got to the point now where it has a 100% detection rate for late stage colonies, which we're defining as colonies over 1.5 millimeters. It will pick up small colonies at day 4 or 5 with a roughly 90% accuracy. And it will detect as a separate object class this very obviously differentiated colony. We can just tell by morphological indications, and it will pick that up as a separate object class. And finally, it will detect polyclonality in these easy examples, where there are 2 macro colonies. You can instantly see that these came from multiple starting cells, no further processing required. The issue in many ways comes from superficially seeming monoclonal colonies, which we don't actually know if they came from a single or multiple cells, i.e. whether they're monoclonal or polyclonal. As an example, we have 2 starting cells here, but a couple of days later, it looks something like this. So we wouldn't know just from the naked eye whether this is a monoclonal colony or a polyclonal colony. And for that reason, we have to go back to the day 1 image, and the same applies to the workflow. So the temptation might be to say, let's train a network to detect single cells in a full well image, but that's just unlikely to happen given how tiny these cells are. As an example, this is just the section where a colony was on the consolidation day. We might be tempted to say that one of these dots here is a cell, but these are actually just pieces of debris which are significantly larger than individual cells, and they're just not visible to the naked eye without zooming in. So what we did is to design a modular workflow which integrates, among other things, the global detection model. So it passes images to the global detection model, which will then extract the coordinates of any colonies in the image. expand those coordinates just a little bit to give us a margin of error, and it will then subset or crop the earlier image of the same well at those coordinates, meaning that the earlier instantiation of the same colony will be approximately centered within the resulting image. So the workflow then just kind of repeatedly does that and passing the resulting images to the intermediate detection model or a local detection model. And like I said, just repeatedly does that until it reaches the day 1 image or the day 0 image, where, assuming everything has gone well, which thankfully it does, the starting or ancestral cell or cells will be approximately centered within the resulting image. So that resulting image can then be passed to our single cell detection model, which will enumerate the number of starting cells in the day 1 image. And on that basis, it can finally be declared monoclonal or polyclonal. This is just kind of like a rough, very broad overview of the workflow, where it will try to reach the day 1 image. If it does, it will count the number of cells. Otherwise, if at any point in that kind of recursive zone shrinking process using the intermediate detection model, if it detects any more than one colony, it will simply declare the well to be polyclonal and cease processing that well. We obviously integrate this with other things such as morphological classification, but I won't have a huge amount of time to go into that here. So otherwise, I'd just like to say a really big thank you to Dan Paul and the Array team, as well as the NICEF Research and Development Leadership team, and everyone at NICEF who helped in this project. It's really been a team effort. And thank you very much, everyone, for listening. I'd be more than happy to take any questions you might have. So thank you very much.